Welcome to the second math lecture, which is going to be on units. Before I even give a definition of units, I want to iterate the importance of them by saying something that my math methods and physics professor told me in my first year of grad school, which is that units are what changes math physics, what differentiates physics from math. So, what are units in the first place? Units are countable concepts. That's really the most general ideal that I can think of, or like the most precise definition. So, example of units which are important in physics are length, time, and mass. So, you can have 1 foot, you can have 1 meter, you can have 1 second or 1 hour, and all of those are units. So the term unit is kind of used interchangeably for the concept, such as length, or for a specific amount of the concept. So length can be called a unit, but so can a mile or a foot or a kilometer. So with this said, we have base units and derived units. So the International System of Units, which is called the SI units, has defined a number of units based on concepts that are measurable and cannot be made up of other units. These are their base units. The meter, which is the unit of length, the kilogram, which is the unit of mass, the second, which is the unit of time, ampere, which is the unit of current, a Kelvin, a unit of temperature, a mole of the number of molecules, and a candela, which is a unit of luminosity or how bright something is. So different systems have different units for the same concept. So the main other competitor for the SI units is the imperial system, which is feet, miles, hours, and so on. And these are the same concepts, but they are technically different units. And then derived units describe concepts which are countable but derived from these base units. So for example, speed is a derived unit of length and time. So speed is measured in meters per second in SI and miles per hour or something akin to that in imperial. So it's dependent on length and the unit of length, and it's dependent on the unit of time. So it is a derived unit instead of a base unit. So rules for working with units are that you can multiply/divide unlike units to form a new unit, but cannot add, subtract, or add or subtract unlike units. So what does it mean to add 50 seconds plus a meter? Doesn't make sense, but it does make sense to talk about 50 meters per second as how fast you're going. If a unit is inside of a function, the argument for that function must be unitless. For example, you can't have sine of t where t is the unit of time because the sine function is a function that allows numbers and outputs numbers. However, sine of omega times t is allowed if omega has units of 1 over time for a total of units of time times 1 over time equals 1, which is a number. So if you have these units, you have to cancel out if you're going to put it in a sine function or an exponential function or a step function or any of these other types of functions that don't just take that basically anything other than addition or multiplication or subtraction or division. So unit analysis, we use brackets to denote the units of a quantity. For example, the unit of meters is length, the unit of a second is time, and the unit of kilograms is mass. So when you have an equation that you think is right, a good way to check to make sure is that the units on either side of the equal sign may match up. So for the equation x equals v times t, where x is distance, which is measured in length, v is speed measured in length divided by time, and t is time. On the left side, we have x equal, the units of x equal to L, which is length. And on the right side, we have the units of v equal to L per time, and the units of t equal to t, or the units of time equal to time, of course. So the units of v times t are the units of v times the units of time, which is going to, after multiplying it out, equal to L times 1, which is equal to L. So X equals VT has units of L on both the left and the right side of the equal sign. So for example, we're going to come up with the definition of F equals MA, which is Newton's second law. We're going to come up with the units that are associated with force, which is F. So the units of F are equal to the units of M times the units of acceleration. So we don't really know what these are yet, but I'll take my word that's mass times length per time squared. So this is just mass times length times time squared times time to the -2, which is 1 over time squared. Or per time squared is another way of writing it. And then for force, there's also something called centripetal motion that we're going to get into, where force is given by mv squared over all. So when we do this, we have force equals the units of mass times the units of speed squared divided by the units of length, which is going to be equal to mass times length divided by time squared divided by length is equal to mass times length squared over t times length is equal to mass, or t squared times length divided by t squared, which gives us the same units of mass times length times t to the -2. So that's just a way that we can check that our assumptions are right, because the units for force in both F equals MA and F equals MV squared over R are going to give you the same units, which means that if nothing else, this is physically something that we can think about. It's something that we can consider to be true.